As you remember, in the last lecture, I talked about the input space partitioning techniques to design test sets from chapter 6 of the Introduction to Software Testing textbook. Probably you know what's the input space partitioning, or ISP, in this context. As I told, this technique could be used in unit testing, integration testing, and system testing equally. This technique is easy to be automated, and no need could be applied with no automation, and there is no need to know about the implementation of the system, or to have the source code of the system. These techniques could be used in black box testing, as I told before. Let me to have a quick overview of previous concepts to remember. We have defined the input the domain as all possible inputs of a program, and input parameters which define the scope of the input domain, which could be extracted by parameter values to a method or all methods of a program. And another type of input parameters is data that is read from a file, or global variables, or other user inputs. All of these constitute the input parameters of a typical program. And we try to partition input domains into some blocks or regions which could have some characteristics, and each characteristic can partition our input domain into some blocks. So we officially define the domain as D, and partition scheme Q of D, which partitions the domain D into a set of disjoint blocks. Each pair of these blocks have no any values in common, which defines disjointness of a pair of blocks. So the blocks must be pairwise disjointness in this partitioning technique, and together the blocks cover the domain. All blocks together should constitute the domain completely. Suppose we have a domain D as this rectangle, and as you see, this domain is partitioned to 3 blocks. Each pair of these blocks have no any value in common, and the intersection of all pairs of these blocks are empty. So these blocks have this disjointness property, and union of these blocks make the domain D. So these two properties should be hold for all partitioning or all applying all characteristics in these techniques. So how we could use these partitions? We can choose a value from each block to test the functionality of our program, and we could forming the partitions by some characteristics of our input parameters. So the first task, the first responsibility of the test engineer is to find characteristics of input parameters, such as case of letters, relationship to special values such as 0 for integer values, integer parameters, and some other semantics of our input parameters. The second responsibility is the partition each characteristic into blocks and form set of blocks. As I told, each pair of them should be disjoint, and all of them constitute the universal domain D. And choose test cases or test sets by combining values from different blocks. For example, some characteristics are illustrated in this slide. Whether an object X is null or not could be one notable characteristics in forming our partitions or our blocks of domain, or some other characteristics you have seen before. Another point is that how we could choose partitions. Defining partitions is not hard, but as I said, it could be get wrong. For example, the order of elements in an input list could trick us, because when we consider the characteristic of the order of elements, we could simply partition the domain into 3 blocks. The blocks B1 for sorted in a sorted list in ascending order. The block P2 consists of includes all lists that are sorted in descending order, and block 3, the third block, includes all lists that have an arbitrary order. As you know, for lists of length 1 or 0, these blocks have some lists in common. They are overlapped with each other. Okay, so the disjointness property is not held in this partitioning, and it's wrong. I told about these boxes before. So in these cases, we could simply consider each characteristics in isolation. For example, the characteristic C1 which partition lists which are in sorted ascending order. By these characteristics, we could partition our domain into two blocks, two disjointness block. The block B1 for characteristic C1 is all lists which are sorted ascending, and block B2 is all lists, includes all lists which are not sorted in ascending order. Okay, the property is true for block B1, but it is false for block B2. So obviously these two blocks could not be overlapped with each other, and could not have some sets in common. And in the second characteristic, the list F sorted in descending order, we have to partition again which are disjoint, and the block B1 for characteristic C2 is the set of all lists that are sorted in descending order, and the block B2 includes all sets that are not sorted in descending order. So to treat with this tricky point, we simply can consider each characteristic in isolation, but in the at first we consider the order of list as one characteristic, but in this step, in the second decision, we consider two isolated characteristics for partitioning. As you know, as I said before, we could have several characteristics to partition the domain and choose our test sets for each partitioning. So the properties, we talk about the properties of partitions, and I think there is no necessary things to talk about, and we have identified in previous lecture 5 steps in ISP or input space partitioning, or in domain modeling. As you know, in the first step we should identify the testable functions from our program, from the program or under test, and as I said, all individual methods are testable functions. Methods in a class often share some characteristics of the class because they could use, all of them can use some properties of the class or some fields of the class in common. Or another property should be considered in this step is that programs have more complicated characteristics. Modeling documents such as UML can be used to design characteristics. This says that several characteristics could be considered or should be considered in domain space partitioning when we use it in black box testing. And so for system testing. In step 2, we just find all parameters. To find all parameters, the parameters, the explicit parameters of each testable function or each method of our program should be considered. All shared variables or shared state of the method or of the program, a program should be considered as input parameters to methods, and state variables of each component could be should be considered as input parameters, or all inputs and file and databases which is used, which are used in the system should be also considered as our parameters in domain modeling. In step 3, we should model the input domain, and I've talked about this step. As you know, this is the most creative design step in these techniques, and the tester should try a lot to design more effective tests. In step 4, in which I'll talk about the step 4 in next session. It's about selecting one coverage criteria in these techniques to apply these techniques to design our test cases, and this could be considered for the next session. And finally, we could refine the combinations of plots to design the final test cases. Until now, if you have any question, you could ask your questions. This is just the point. I finished my lecture in previous session. We define the type of each block before testing. Yes. First of all, in this technique, we should define the characteristics that can help us to partition our domain. In this session, if you have any question, we start the new materials for this session. In this session, we talk about just about two approaches of input domain modeling. We have two approaches to do modeling regarding to the input domain. The first approach is interface-based approach, and the second one is functionality-based approach. I will talk with details in these two approaches in this session. When we use this approach, we have no need to the source code of the program, or just in black box testing, in which we have little documentation about the methods or about the functionality of our program. We could use simply this approach. But then we have more details about the functionality of the program. It's better to use this approach. But what is the interface-based approach and functionality approach? In interface-based approach, develop characteristics. We could develop characteristics directly from individual inputs. We consider each input parameter in isolation in this approach, and we treat the input with the input parameters more mechanically, and we consider some characteristics such as the relationship of them with special values, with specific values. For example, if we have a method which receives two integer parameters, we simply consider the characteristics of the relationship of each parameter with 0. So we could have simply three blocks for each parameters. The first block, the values which are less than 0. The second, the blocks that consists just 0 element, and the third block consists of values which are greater than 0. So in this approach, we treat mechanically with our input parameters and consider each of input parameters in isolation. So this is the simplest application method for input domain modeling, and can be partially automated in some situations because there is no need to inference about some concepts. There is no need to analyze the semantic of input parameters. There is no need to consider the relationship of input parameters and the dependency or the effect of each parameter to other parameters. So this approach could be done easy and could be automated and could be done mechanically. But in functionality-based approach, we need to know more about our parameters, and in this approach we should consider some characteristics about the behavioral view of the program. We should know the preconditions and postconditions of each method of the program, and we should know about what is each input parameters and what is its functionality or their functionalities. Okay, and what about the relationship of a method parameters, the relationship between each method parameters. Okay, so this is more complicated. This approach could be more complicated than the first approach, because in this approach we should analyze the semantic of each input parameter, the relationship between parameters, the functionality of each method, the functionality of a program, and so on. So this approach is harder to develop and requires more design effort for test engineers. But it may result in better tests. It's trivial when we do more effort, we expect better results. So there is no problem in this sense, and this approach could lead to a better test cases or fewer tests that are as effective. Okay. This is not enough about this approach. We should discuss with more details about these approaches in next slides and explain them by using some illustrative examples. So let me Let's go to the next slides and talk with more details about this approach. In interface-based approach, as you see in this slide, we could mechanically consider each parameter in isolation, as I told in previous slide. This is an easy modeling technique and relies mostly on syntax. The syntax in doing this approach in automation, we could review our definition or interfaces of our methods and consider just the syntax of our methods. The syntax of our methods could be defined by their return values and their input parameters. And there is no need knowledge about the functionality of each method. We just treat mechanically with this syntax, with this definition of our methods. Some domain and semantic information won't be used in this approach. There is no need to knowledge about the semantics of our parameters or domain of the program. But one of the disadvantages of this approach is that it could lead to an incomplete model, incomplete partitioning, because we have not considered the semantics of our parameters. And in this approach, we usually ignore relationship among parameters, because there is no knowledge about the semantic of parameter or their relationships. Let me ask this comment: if it is hard to developers, how is used? It's hard for automation. It's harder for automation, not for developers. I talked about the hardness of designing automated tools for designing test cases, but it could be easy for developers, as I will see soon by some examples. We will conclude that it could be easy for developers, but it could be hard for automation, because when we consider the semantic of input parameters, automation tools could not consider the semantics easily. Okay. So, for example, we consider a simple example from Jeff Offwood website. Let me to go to this page. Consider we have a method. Which keep the length of sides of any triangle, and it was expected to detect the type of the triangle. As you know, we could have three type of triangles, which consists of the scalene triangle, the isosceles triangle, and equilateral triangle. In this triangle, three sides of the triangle should be equal. In this triangle, in this type of triangle, two sides should be equal. And in the scalene triangles, there is no relationship, any meaningful relationship between the equality of any sides of triangles. So there is three types of triangles, and we want to design a method to detect the type of any triangle. And we could consider simply an invalid triangle. Maybe our input could not form any triangle. For example, if you consider a triangle with a side 0, a side 1, and a side 2, you know that we have no triangle with a side of length 0. Okay, so it's possible to feed the method with invalid parameters. So altogether we have four types of triangles: scalene, isosceles, and equilateral triangle, and the last type is invalid triangle. So suppose we have a program which take the length of three sides of each triangle, which receive the length of each sides of the triangle, and tell us about the type of the triangle. For example, in a typical implementation of this functionality, we could define a class such as triangle type. Okay, and in this class we should define a method to detect the type of triangle. In this method, we should send three parameters. The first parameter is the length of side 1, the second is the length of side 2, and the third one is the length of the third side of a triangle. Okay, all of these slides is considered as integer value. We simply define these sides as integer lengths. Okay. When we have an invalid triangle, when these sides could be defined as invalid value. For example, when we set these parameters, each of these parameters to a value such that is less than 0, we have an invalid triangle, because there is no triangle with a negative length for each side of the triangle. Okay, so in the first step, we should check if this combination of input parameters is feasible or not. When each of these parameters is less than 0, we could not define a valid triangle by these parameter values. So in the first step, we check the values of each parameter to be greater than 0. If not, we simply return the invalid type. And in the second step, we check the triangle inequality. When the sum of the lengths of two sides is less than the length of the third side, this combination could not define a valid triangle. In this step, we also check another type of invalid triangles. Okay, invalid parameters as sides of a triangle. Okay, and in the third step, we check about the equilateral triangles. When all sides of triangle have the same length, we have an equilateral triangle. So if side S1 equals with S2 and S2 equals with S3, all sides have the same value, all parameters have the same value, we could return equilateral triangle. And in the fourth step, we try to check if the triangle, if the input sides make isosceles triangle or not. If two of these sides, these three sides be equal, we have a isosceles triangle. Okay, and finally, if none of these conditions is true, we could return scaling triangle. Okay, this is a program for detecting the type of triangle, and we consider this as our example to design or to model our input domain by the two approaches: interface